Did you know that time itself can stretch and twist like a piece of rubber near a black hole? This isn't science fiction, it's the reality of space-time, the very fabric of our universe. Space-time isn't just a distant concept studied by physicists. It's the hidden framework that governs everything from the motion of planets to the way we experience time itself. In this video, we're diving into 50 astonishing facts about space-time that will challenge everything you thought you knew about reality. From mind-bending paradoxes to cosmic mysteries, each fact will take you deeper into the wonders of the universe. And here's a taste of what's ahead. The first fact explores how time can slow down or speed up depending on where you are in the cosmos. Ready to have your mind blown? Let's begin this journey together. Let's take a step back, way back, to the very beginning when space and time as we know them didn't even exist. The story of space-time starts with the Big Bang, an event so monumental it's hard to wrap your head around. Around 13.8 billion years ago, everything in the universe was compressed into an unimaginably small point called a singularity. This wasn't just a tiny dot of matter, it was a point where the laws of physics as we understand them break down. From this singularity, the universe began expanding at an astonishing rate, and with it, space and time were born. But here's where it gets mind-bending. Space and time aren't separate entities. They're woven together into a single fabric we call space-time. Think of it like the surface of a trampoline. When you place something heavy on it, the surface bends and stretches. In the same way, massive objects in the universe bend and distort space-time, creating what we experience as gravity. This idea, first introduced by Einstein, revolutionized how we understand the cosmos. Yet, despite all we've learned, the singularity remains one of the universe's greatest mysteries. Why did it exist? What triggered the Big Bang? And perhaps the most perplexing question of all, what came before it? Did time even exist before that moment? These questions might sound philosophical, but they're at the heart of modern physics. As we ponder these mysteries, it's worth reflecting on how the Big Bang set the stage for everything that follows. From the tiniest particles to the vast galaxies we see today, the universe's rapid expansion created the framework for all of existence. And as we'll see next, this framework isn't just a static backdrop, it's dynamic, shaped by the curvature of space-time itself. What if the way you perceive time and space isn't the whole story? That's exactly what Albert Einstein proposed with his theory of relativity, a groundbreaking idea that completely reshaped our understanding of the universe. Before Einstein, gravity was seen as a simple force pulling objects together. But he introduced a radical new concept. Gravity isn't just a force, it's the result of space and time bending around massive objects. Think of space-time as a trampoline. Place a bowling ball in the center and the fabric stretches and curves around it. Now roll a marble across the surface and its path will bend as it moves toward the ball. That's essentially what happens in space. Planets, stars, and even light follow these curved paths, not because of a mysterious force, but because space-time itself is warped by mass. One of the most astonishing predictions of Einstein's theory is the bending of light. Imagine a beam of light traveling through space. When it passes near a massive object like a star, its path curves slightly around it. This phenomenon, called gravitational lensing, has been observed in space countless times. Astronomers use it to study distant galaxies that would otherwise be too faint to see, as the light from these galaxies bends around massive objects in the foreground, acting like a cosmic magnifying glass. This isn't just theoretical, it's real, observable proof that space-time is flexible, like the trampoline in our metaphor. But Einstein's theory doesn't stop there. It opens the door to even more mind-bending ideas like the concept of time dilation. What if time itself isn't constant? What if it can stretch and slow down depending on where you are or how fast you're moving? This isn't science fiction, it's a direct consequence of the way space-time works. and it leads us to even stranger phenomena that continue to challenge our understanding of reality. Here's a natural continuation of the script. Grab your seat because we're about to dive into one of the most mind-bending concepts in physics, the twin paradox. Picture this: identical twins, one stays on Earth and the other rockets off into space at nearly the speed of light. When the traveling twin returns, they've aged significantly slower than their Earth-bound sibling. Sounds like science fiction, right? But this isn't just a wild idea. It's rooted in Einstein's theory of relativity and something called time dilation. Here's the science behind it. As an object moves closer to the speed of light, time literally slows down for it compared to a stationary observer. This isn't just theoretical, it's been proven with atomic clocks. Scientists have placed ultra-precise clocks on airplanes and compared them to clocks on the ground. Sure enough, the clocks on the fast-moving planes ticked slightly slower. It's a tiny difference, but it's real. Now, here's where it gets even more fascinating. This isn't just a cool thought experiment, it has real-world applications. Take GPS satellites, for example. They orbit Earth at high speeds, and because of time dilation, their onboard clocks would drift out of sync with ground-based clocks if we didn't account for it. Without correcting for this effect, your navigation system would be off by miles. So, what does this tell us? Time isn't the fixed, unchanging thing we often think it is. It's flexible, shaped by motion and gravity, and this paradox is just the tip of the iceberg when it comes to understanding the strange nature of time. Speaking of which, let's take a closer look at what time actually is and how it intertwines with the fabric of the universe. Did you know that, according to Einstein, traveling to the future isn't just science fiction, it's a scientific possibility? His theory of relativity tells us that time isn't as fixed as it seems. In fact, time can stretch or shrink depending on how fast you're moving or how close you are to something incredibly massive. This means that if you could travel close to the speed of light, time would slow down for you compared to someone standing still. When you finally stopped, you'd find yourself in the future. Sounds wild, right? Take astronauts, for example. Even though they're not traveling anywhere near the speed of light, they're still moving much faster than we are on Earth. And because of this, they experience time slightly differently. After spending months on the International Space Station, astronauts return home having aged just a tiny bit less than the rest of us. It's a minuscule difference, but it's proof that time can behave in unexpected ways. Now, imagine what might happen if we could build a spacecraft capable of reaching those extreme speeds. Could we one day create a vessel that lets us leap decades or even centuries into the future? While it's a tantalizing idea, the reality is that we're still far from having the technology to make it happen. And even if we could, there's a catch: you can't go backward. Time travel to the future might be possible, but returning to the past is a whole other challenge. What if you could step back in time and witness history unfold firsthand? The idea of traveling to the past has fascinated humanity for centuries, but is it really possible? According to some theories in physics, the answer might be maybe, but with some mind-bending caveats. One of the most intriguing concepts involves wormholes, those hypothetical tunnels through space-time. If a stable wormhole could exist, some scientists suggest it might allow for a shortcut not just through space, but also through time. Imagine stepping into one end and emerging decades or even centuries earlier. Sounds like science fiction, right? Yet, the math doesn't entirely rule it out. Another theoretical pathway is something called a closed time-like curve, a loop in space-time that could, in theory, allow an object or person to travel back to their own past. It's a dizzying idea, but it comes with a catch: paradoxes. The most famous of these is the grandfather paradox, where a time traveler goes back and prevents their own birth, creating a logical contradiction. If you were never born, how could you have traveled back in time in the first place? These paradoxes aren't just plot holes for sci-fi writers, they're serious scientific roadblocks. Most physicists argue that past time travel is impossible precisely because of these inconsistencies. Nature seems to have a way of preventing paradoxes, maintaining the integrity of cause and effect. So, why does this idea still capture our imagination? Perhaps it's because space-time itself is so mysterious and full of possibilities. The very fabric of the universe might hold clues we're only beginning to uncover. Could the answers to these cosmic riddles lie hidden in the twisting, bending nature of space-time itself? As we continue to explore, the mysteries of our universe only grow deeper and more fascinating. What if you could take a shortcut across the universe, bypassing the vast distances that light itself takes eons to cross? Enter the fascinating concept of wormholes, often described as cosmic tunnels through the very fabric of space-time. These theoretical passages could, in principle, connect two distant points in the universe, or even different points in time, creating a bridge that defies our everyday understanding of distance and duration. Picture it like folding a piece of paper and poking a hole through the layers. Instead of traveling the long way around, you'd simply step through. But here's the catch. While wormholes are mathematically possible within the framework of Einstein's theory of general relativity, they're far from being something we could casually stroll through. For one, stabilizing a wormhole would require an exotic form of energy or matter with negative mass, something we've yet to discover in the universe. And even if we could find it, the amount of energy needed to keep a wormhole open is staggering, potentially more than what an entire galaxy produces. It's a reminder that while the cosmos offers tantalizing possibilities, it also presents monumental challenges. And speaking of challenges, the nature of space-time itself becomes even stranger when we zoom in to the quantum level, where the rules of reality seem to bend in ways that defy our intuition. Picture the surface of a calm lake, smooth and undisturbed. Now imagine that same lake boiling, with bubbles constantly forming and popping in a chaotic dance. This bubbling chaos is a bit like what scientists think space-time might look like at the tiniest scales, a phenomenon known as quantum foam. At levels so small that even atoms seem giant, space-time isn't the neat, orderly fabric we often imagine. Instead, it's a turbulent, ever-changing sea of fluctuations. This idea completely upends our classic view of space-time as something stable and predictable. Instead, it suggests that the very foundation of the universe is alive with activity, constantly shifting in ways that defy our everyday experience. The concept of quantum foam challenges not just our intuition but also the way we understand physics. In classical physics, space and time are smooth and continuous, like a blank canvas waiting to be painted. But in the quantum realm, that canvas is more like a seething ocean, with tiny ripples and waves that appear and vanish in an instant. These fluctuations are so small and short-lived that they're impossible to observe directly, but their effects ripple through our understanding of the cosmos. This turbulence at the smallest scales hints at a universe far more dynamic and unpredictable than we've ever imagined. So, what does this mean for the big picture? These tiny quantum effects might play a surprising role in shaping the universe as a whole. Just as the smallest waves can eventually build into a tsunami, the constant churning of quantum foam could have profound implications for how space-time behaves on larger scales. It's a reminder that the universe operates on many levels, from the vastness of galaxies to the tiniest flickers of existence, and each one is deeply connected in ways we're just beginning to explore. What if everything we perceive as reality, every star, planet, and galaxy, is actually a hologram? This is the mind-bending idea behind the holographic principle, a theory that suggests our entire three-dimensional universe might be encoded on a two-dimensional surface. Imagine the cosmos as a massive cosmic projector, casting the illusion of depth and volume from a flat screen. This principle doesn't just challenge our understanding of space-time, it completely redefines it. At its core, the holographic principle proposes that all the information about what happens inside a region of space can be thought of as being stored on its boundary, much like how a hologram encodes a 3D image on a 2D surface. This theory has its roots in the study of black holes, where it was discovered that the amount of information a black hole can store is proportional not to its volume but to the area of its event horizon, the boundary beyond which nothing can escape. If this is true for black holes, could it apply to the universe as a whole? The implications are staggering. It suggests that the fabric of reality might be far simpler and stranger than we ever imagined. Instead of an endless expanse of space, our universe could be a vast, intricate tapestry of information woven into the fabric of a two-dimensional surface. But what does this mean for our understanding of reality? If the holographic principle holds, it could mean that everything we experience, time, space, even our own consciousness, is just a projection of that underlying information. It's a thought that blurs the line between the physical and the abstract, raising questions about the nature of existence itself. And while this idea might sound like science fiction, it's grounded in rigorous physics, with experiments and observations continuing to explore its validity. Speaking of black holes, their role in this theory is crucial. The way space-time behaves near these cosmic giants is already bizarre, but the holographic principle adds another layer of mystery. It suggests that black holes might be the key to unlocking the true nature of reality, acting as windows into the two-dimensional fabric that underpins everything. So, as we ponder the holographic universe, let's take a closer look at what happens to space-time when it gets too close to a black hole, a journey that will push our understanding of physics to its limits. Picture this, a region in space where gravity is so intense that it bends the fabric of reality itself. This is the heart of a black hole, a cosmic phenomenon that challenges our understanding of space and time. At its core, a black hole isn't just an object, it's a distortion, a place where the rules of physics as we know them begin to break down. The gravity here is so powerful that it warps space-time into an inescapable pit, dragging everything within its grasp toward its center. One of the most fascinating features of a black hole is its event horizon, the point of no return. Imagine standing on the edge of a waterfall. Once you step over, there's no going back. The event horizon works in a similar way. Once anything, whether it's matter, energy, or even light, crosses this boundary, it's lost forever, unable to escape the black hole's immense gravitational pull. This is why black holes appear utterly dark. Not even light can break free to reach our eyes. But what lies beyond the event horizon? What happens inside a black hole? This question has puzzled scientists for decades and remains one of the greatest mysteries in astrophysics. Some theories suggest that at the center of a black hole lies a singularity, a point where density becomes infinite and the laws of physics as we know them cease to function. It's a place where space and time collapse into something beyond our comprehension. This mind-bending idea leads us to ponder the true nature of the universe and the limits of human understanding. As we explore these cosmic enigmas, we're reminded of how much there is still to discover. The journey into the heart of a black hole might be one we can never fully map, but it's a path that continues to inspire awe and curiosity. At the heart of a black hole lies a point of infinite density and gravity, a place where the very fabric of space-time unravels. This is a singularity. Here, the laws of physics as we know them collapse, and the equations that govern our universe reach their limits. Singularities are not just a feature of black holes, they also play a crucial role in our understanding of the Big Bang, the moment when the universe itself began. In both cases, these bizarre regions mark the edge of our scientific knowledge, where space and time seem to vanish into the unknown. Studying singularities is a monumental challenge. They are hidden behind the event horizons of black holes, shrouded in mystery and inaccessible to direct observation. Even the most advanced theories, like general relativity, fail to explain what truly happens at these points. Some scientists speculate that quantum mechanics might hold the key, but merging these two frameworks remains one of the greatest puzzles in physics. As we grapple with these cosmic mysteries, one question emerges: what happens to space-time in the presence of exotic matter? This strange substance, which defies the usual rules of physics, might hold clues to understanding the extreme conditions near singularities. And that's where our journey takes us next. Picture this, a type of matter so strange, it doesn't just bend the rules of physics, it shatters them entirely. Exotic matter, as it's called, is a hypothetical substance with properties that seem straight out of science fiction. Unlike the matter we're familiar with, exotic matter possesses negative energy, meaning it doesn't attract objects gravitationally, it repels them. This bizarre characteristic could hold the key to one of the most tantalizing ideas in physics: stabilizing wormholes. Imagine a shortcut through space-time, a tunnel connecting two distant points in the universe. While wormholes are theoretically possible, they'd collapse instantly without something to keep them open. That's where exotic matter comes in. Its negative energy could counteract the forces trying to crush the wormhole, making it a potential gateway for interstellar travel. But here's the catch: exotic matter defies everything we know about the laws of physics. It's not something we've ever observed or created, and its existence remains purely theoretical. Yet, if it does exist, it could revolutionize our understanding of the cosmos. The question is, could the universe actually produce such a substance? The answer lies in the mysteries of quantum mechanics and the wild frontiers of theoretical physics. As we ponder the possibilities, let's shift our gaze to another mind-bending phenomenon: the relentless expansion of the universe. Imagine you're watching a loaf of bread rise in the oven. As the dough expands, the raisins embedded in it move farther apart, not because they're actively traveling, but because the space between them is stretching. This is a simple way to picture what's happening to our universe. Galaxies, like those raisins, are drifting away from each other as the fabric of space-time itself expands. It's not that galaxies are moving through space, it's that space itself is growing, carrying them along with it. This expansion isn't just happening, it's speeding up. Scientists believe a mysterious force called dark energy is responsible for this acceleration. Think of dark energy as the unseen hand that's pushing the universe apart faster and faster over time. It's one of the greatest puzzles in modern cosmology, making up about 68% of the universe's energy content, yet we still don't fully understand what it is or how it works. What's particularly fascinating is that this expansion isn't uniform. While galaxies are moving apart on a cosmic scale, gravity keeps them bound together in clusters like islands in an ever-growing ocean. This tug-of-war between the relentless pull of dark energy and the binding force of gravity shapes the large-scale structure of the universe. As we observe this phenomenon, we're left to wonder, what does this mean for the ultimate fate of space-time? Could this expansion continue forever, or is there a tipping point we've yet to discover? When we ponder the ultimate fate of the universe, two dramatic possibilities emerge, each as mind-bending as the other. On one hand, there's the Big Crunch, a scenario where the expansion of the universe reverses, pulling everything back into a singular point. Picture space-time itself collapsing, galaxies rushing toward one another, and all matter and energy compressed into an unimaginably dense state. It's like hitting rewind on the Big Bang, returning the cosmos to its origin. But on the other hand, we have the Big Freeze, where the universe continues to expand indefinitely. In this case, space-time stretches thinner and colder over time. Stars burn out, galaxies drift apart, and the cosmos fades into a vast, dark emptiness. So, what evidence supports these theories? The Big Crunch hinges on the idea of gravity eventually overcoming the force driving expansion. If there's enough matter in the universe, gravity could slow expansion and eventually reverse it. But here's the twist. Observations of distant supernovas suggest the universe is not just expanding, it's accelerating. This discovery points to dark energy, a mysterious force pushing the cosmos apart, making the Big Crunch seem less likely. Meanwhile, the Big Freeze aligns with this accelerating expansion, painting a picture of a universe growing colder and more diffuse as eons pass. Both scenarios have profound implications for space-time. The Big Crunch would mark the end of space-time as we know it, a cosmic reset. The Big Freeze, however, suggests an eternal expansion where space-time stretches into infinity, becoming a frozen, lifeless void. Which of these futures feels more plausible to you? It's a question that challenges our understanding of the universe and its ultimate destiny. As we grapple with these possibilities, it's impossible not to wonder what role dark matter plays in shaping this cosmic story, leading us perfectly into our next exploration. Imagine a force so powerful it shapes the entire universe, yet remains completely invisible. That's the enigma of dark matter. Even though we can't see it, dark matter plays a crucial role in bending and warping space-time through its gravitational pull. This invisible substance makes up about 85% of all matter in the cosmos, acting like an unseen scaffold that holds galaxies together. Without dark matter, galaxies would simply fly apart, unable to maintain their structure. Its gravitational influence is so profound that it dictates the formation of galaxy clusters and even the large-scale structure of the universe itself. Scientists have long been fascinated by this mysterious component of the cosmos. While it doesn't emit, absorb, or reflect light, its presence is inferred by the way it bends the path of light from distant objects, an effect known as gravitational lensing. This phenomenon allows astronomers to map the distribution of dark matter across the universe, revealing its intricate web-like structure. Yet, despite decades of research, dark matter remains elusive. Countless experiments are underway, from deep underground detectors to particle colliders, all aimed at uncovering its true nature. As we continue to search for answers, one thing is clear: dark matter's influence on space-time is undeniable. It's a reminder that the universe is full of mysteries waiting to be unraveled. And just as dark matter shapes the cosmos in ways we're still trying to understand, space-time itself behaves in extraordinary ways under extreme conditions that push the boundaries of our imagination and challenge everything we think we know. Neutron stars are some of the most extreme objects in the universe, packing the mass of a star into a sphere no larger than a city. These dense remnants of supernova are so compact that a single teaspoon of their material would weigh billions of tons. But it's not just their density that's mind-bending, they also warp the fabric of space-time itself. Imagine space-time as a vast, stretchy sheet, and a neutron star as a heavy bowling ball placed on it. The sheet bends and twists around the star, creating a deep well of gravity. Now add something even more fascinating. Neutron stars spin incredibly fast, some completing hundreds of rotations every second. This rapid rotation doesn't just move the star, it drags space-time along with it, a phenomenon known as frame dragging. Picture a spoon swirling through a jar of honey. As the spoon turns, the honey clings to it, twisting and flowing in the same direction. In a similar way, the neutron star's spin pulls space-time into a swirling vortex around it, distorting the very fabric of the universe. This effect is so powerful that it can alter the paths of nearby objects, bending light and even time itself. And here's where things get even stranger. The disturbances caused by these rotating neutron stars don't stay local. They ripple outward, creating gravitational waves that travel through the cosmos, carrying with them the echoes of these incredible cosmic events. Imagine dropping a stone into a still pond and watching the ripples spread outward. Now picture something far more dramatic: two massive black holes colliding in the depths of space. This collision doesn't create ripples in water, but in the very fabric of space-time itself. These ripples are called gravitational waves, and they're one of the most extraordinary phenomena predicted by Einstein's theory of general relativity. In 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, made history by detecting these waves for the first time, proving Einstein right once again. But how does LIGO detect something as subtle as a ripple in space-time? The observatory uses incredibly precise lasers to measure tiny distortions caused by passing gravitational waves. When a wave travels through, it stretches and compresses space-time itself, shifting the distance between mirrors in LIGO detectors by less than the width of an atom. This groundbreaking discovery didn't just confirm a century-old prediction. It opened an entirely new way to study the universe. Before, we relied on light to observe cosmic events. Now, gravitational waves let us listen to the universe, revealing phenomena we couldn't see otherwise, like black hole mergers or neutron star collisions. The implications are profound. Gravitational waves have given us a deeper understanding of the universe's most violent and energetic events. They've also provided clues about the nature of gravity itself, helping us test and refine Einstein's theories in extreme conditions. What's even more fascinating is that this discovery hints at the possibility of other dimensions. Space-time, as we understand it, is a four-dimensional fabric, 3 dimensions of space and 1 of time. But could gravitational waves reveal hidden dimensions beyond our perception? This question brings us closer to understanding the true nature of our universe and how space-time behaves in ways we're only beginning to explore. What if everything we know about the universe is just the tip of the iceberg? String theory, one of the most fascinating concepts in modern physics, suggests exactly that. It proposes that beyond the familiar 3 dimensions of space and 1 of time, there are additional dimensions, hidden layers of reality we can't perceive. These extra dimensions, possibly as many as 10 or 11, are thought to be curled up or compactified at scales so tiny they're beyond our ability to detect. Think of them like the threads of a tightly wound ball of yarn, invisible to the naked eye but essential to the fabric of the universe. This idea isn't just a wild guess, it's a mathematical necessity for string theory to work. According to the theory, the fundamental building blocks of the universe aren't particles but tiny vibrating strings. These strings can vibrate in different ways, giving rise to the particles and forces we observe. But for the math to add up, these strings need more room to move, hence the need for extra dimensions. It's like trying to play a symphony with only 4 notes. The melody only makes sense when you add the missing keys. So where are these extra dimensions? If they exist, they're likely compactified at the Planck scale, which is about 1/trillionth of a trillionth of a trillionth of a meter. To put that into perspective, if an atom were the size of a football stadium, the compactified dimensions would be smaller than a single grain of sand on the field. This extreme scale makes them incredibly difficult to detect, leaving us with the challenge of finding indirect evidence to support string theory's bold claims. The implications of extra dimensions on space-time are profound. They could explain why gravity is so much weaker than the other fundamental forces. It might be leaking into these hidden dimensions. They could also provide a framework for unifying all the forces of nature into a single, elegant theory, a goal physicists have been chasing for decades. Yet for all its promise, string theory remains just that, a theory. Without experimental proof, it's a tantalizing idea that hovers on the edge of scientific validation. And while we grapple with the mysteries of extra dimensions, it's impossible not to wonder about the very nature of time itself. Is time just another dimension, or is it something far more complex? This question leads us to the next intriguing fact about space-time, a fact that challenges our understanding of reality itself. Have you ever wondered why time seems to flow only one way? No matter how hard we try, we can't rewind the clock or return to yesterday. This one-way journey of time, often called the arrow of time, is one of the most intriguing puzzles in physics. At its core, this phenomenon is deeply connected to a concept called entropy, a measure of disorder in the universe. Entropy always increases over time, and it's this relentless march toward disorder that gives time its direction. Think of it like a shattered glass. Once it breaks, it doesn't spontaneously reassemble itself. That's entropy at work, steering the universe from order to chaos. But here's a mind-bending question. Could time ever reverse? If entropy somehow decreased, would the arrow of time flip? While theoretically possible, the odds of this happening are astronomically low. The universe seems to have a built-in preference for moving forward, not backward. Yet, this idea opens the door to fascinating possibilities, especially when we consider phenomena like time crystal structures that defy our usual understanding of time and entropy. Speaking of which, picture this, a crystal that doesn't just repeat in space like the patterns in a diamond, but one that repeats in time. This isn't science fiction, it's a real phenomenon known as a time crystal. Unlike ordinary crystals, which arrange their atoms in a repeating pattern across space, time crystals exhibit a repeating pattern in time. They're like clockwork, oscillating in a stable rhythm without any energy input, almost as if they've tapped into a perpetual motion machine. This bizarre behavior defies traditional physics, particularly the second law of thermodynamics, which states that systems naturally move toward disorder over time. Time crystals, however, manage to stay in a stable, repeating state indefinitely, challenging everything we thought we knew about the nature of time and matter. The discovery of time crystals was nothing short of groundbreaking. In 2016, physicist Frank Wilczek first proposed the idea, but it wasn't until 2017 that researchers successfully created them in a lab using quantum systems like trapped atoms and superconducting qubits. These experiments confirmed that time crystals aren't just theoretical, they're a new state of matter, opening up a world of possibilities. Imagine quantum computers that can operate with unprecedented stability, or sensors that can detect minute changes in their environment with incredible precision. The potential applications are vast, but what's even more fascinating is how time crystals force us to rethink the very fabric of reality. By existing in a state that repeats in time rather than space, time crystals blur the line between the temporal and the spatial. They suggest that time itself might have a structure, almost like a dimension we can manipulate. This idea challenges our classical understanding of space-time, where time is seen as a constant, unidirectional flow. Instead, time crystals hint at a universe where time could be broken down into discrete, repeating units, much like the way space is divided into atoms or molecules. But here's where it gets even more intriguing. The creation and behavior of time crystals are deeply tied to quantum entanglement, a phenomenon where particles become so deeply connected that the state of one instantly influences the state of another, no matter the distance. This entanglement is what allows time crystals to maintain their rhythmic patterns, and it's also a key player in our understanding of space-time itself. As we delve deeper into the mysteries of quantum mechanics, we're beginning to see how entanglement might weave the very fabric of the universe, connecting space and time in ways we're only starting to comprehend. Einstein once referred to quantum entanglement as spooky action at a distance, and for good reason. Imagine two particles separated by vast cosmic distances, yet somehow linked in a way that defies our everyday understanding of space and time. When one particle's state changes, the other reacts instantaneously, as if distance doesn't exist. This bizarre connection happens faster than the speed of light, a speed limit Einstein himself thought was unbreakable. It's as though the universe has a secret line of communication that bypasses the rules we've come to accept. This phenomenon doesn't just challenge classical physics, it outright defies it. How can something happen instantaneously across light years without violating the laws of relativity? The answer lies in the strange, counterintuitive world of quantum mechanics, where particles don't play by the same rules as the objects we see around us. Could this entanglement be harnessed for faster-than-light communication, allowing us to send messages across the galaxy in an instant? While the idea is tantalizing, scientists have yet to crack the code, and many believe the universe's rules might prevent it altogether. This strange connection between particles hints at a deeper layer of reality, one that might even tie into the concept of a multiverse. Speaking of which, what if our universe isn't the only one out there? What if there are countless others, each with its own set of rules and dimensions? The mysteries of quantum entanglement might just be the tip of the iceberg. What if everything we know as reality is just one tiny piece of an infinitely larger puzzle? This is the mind-bending idea behind the multiverse theory, the notion that our universe might not be the only one out there. Imagine a cosmic tapestry woven with countless universes, each with its own unique space-time structure, physical laws, and even alternate versions of you and me. It's a concept that sounds like science fiction, but it's rooted in serious scientific exploration. Physicists have proposed several types of multiverses, each offering a different perspective on this staggering idea. For instance, there's the bubble multiverse, where universes float like soap bubbles in an endless cosmic foam, each expanding in its own direction. Then there's the parallel universe idea, where every decision you make splits off into a new reality, creating infinite timelines. And let's not forget the mathematical multiverse, which suggests that every possible mathematical structure exists as its own universe. While these theories are fascinating, it's important to note that they remain highly speculative. We don't yet have the technology or evidence to confirm the existence of other universes, but the possibilities are endlessly intriguing. What's even more mysterious is the force that might be driving the expansion of our own universe, dark energy. Could this enigmatic force be connected to the existence of other universes? The more we explore, the more questions arise, pulling us deeper into the cosmic unknown. Picture this: the universe isn't just expanding, it's speeding up. That's where dark energy comes into play, a mysterious force that makes up about 68% of the universe. Unlike gravity, which pulls things together, dark energy acts like an invisible push, stretching space-time faster and faster over time. But what exactly is it? Scientists are still scratching their heads. It could be a property of space itself, a kind of energy woven into the fabric of the cosmos. Or maybe it's something entirely beyond our current understanding. What we do know is that dark energy is shaping the fate of the universe. If it continues to dominate, galaxies will drift farther apart, and the cosmos could end in a cold, empty expanse known as the Big Freeze. But before we dive deeper into that chilling possibility, let's rewind the clock to one of the earliest snapshots of the universe, the cosmic microwave background. Picture this: a faint glow, almost imperceptible, permeating every corner of the universe. This is the cosmic microwave background, the oldest light in existence, and it's our direct link to the infancy of the cosmos. Born just 380,000 years after the Big Bang, this afterglow captures a moment when the universe cooled enough for light to travel freely for the first time. It's like a photograph of the universe in its earliest days, frozen in time and etched into the fabric of space. What makes the cosmic microwave background so extraordinary is the story it tells about space-time itself. The tiny fluctuations in this ancient light reveal the seeds of structure in the universe, slight variations in density that would eventually grow into galaxies, stars, and planets. These patterns are not just random, they're a map of how space-time was shaped in those initial moments, a blueprint of the universe's architecture. The discovery of the cosmic microwave background in the 1960s was a massive win for the Big Bang theory. Before this, the idea of a universe born from an explosive event was just one of many competing ideas. But this faint glow, detected by accident by two scientists using a radio telescope, became the smoking gun. It confirmed that the universe had a beginning, a moment when everything we know, space, time, and energy, burst into existence. But the cosmic microwave background doesn't just tell us about the past, it also helps us understand how space-time evolves. Those early fluctuations in density imprinted on this ancient light set the stage for the universe's expansion and the formation of galaxies. Without the interplay of space and time, gravity couldn't have worked its magic, pulling matter together to create the cosmic structures we see today. This faint glow, billions of years old, is a testament to the intricate dance of space-time that shaped everything we know. As the universe expanded after the Big Bang, space-time itself began to warp and ripple, setting the stage for one of the most extraordinary events in cosmic history, the birth of galaxies. These distortions in space-time acted like invisible scaffolding, guiding the distribution of matter and energy across the cosmos. But what exactly shaped these early structures into the galaxies we see today? Enter dark matter, an unseen yet incredibly powerful force. While dark matter doesn't emit light or interact with electromagnetic forces, its gravitational pull was crucial in gathering gas and dust into dense clouds, which eventually collapsed under their own gravity to form the first galaxies. Think of it like this: if space-time is a vast, stretchy fabric, dark matter is the weight that creates deep dents in that fabric. Ordinary matter, like the gas and dust that make up stars and planets, naturally flows into these dents, pooling together to form galaxies. Gravity, acting as the architect, then sculpted these massive collections of matter into the intricate spirals, ellipticals, and irregular shapes we observe. But here's a fascinating question for you. How did these first galaxies manage to form in such a relatively short cosmic time frame, just a few 100 million years after the Big Bang? The answer lies in the delicate interplay between space-time, dark matter, and gravity, a trio that continues to shape the universe even today. And speaking of shaping the universe, let's shift our focus to another fundamental aspect of space-time: the speed of light, a constant that not only defines how fast light travels, but also how we perceive the very fabric of reality itself. Did you ever wonder why nothing in the universe can outpace light? It's not just a rule, it's a fundamental feature of space-time itself. The speed of light, roughly 300,000 kilometers per second, acts as the universe's ultimate speed limit. But why? It all ties back to the fabric of space-time and the way it governs cause and effect. When objects move faster, time slows down for them, and space contracts according to Einstein's theory of relativity. But as you approach the speed of light, these effects become so extreme that reaching or exceeding it would require infinite energy and lead to impossible paradoxes, like breaking the laws of causality, where events could happen before their causes. What if something could surpass this limit? Enter tachyons, hypothetical particles that, if they exist, would always move faster than light, challenging our understanding of reality. But more on that intriguing possibility in just a moment. What if we told you there might be particles out there that don't just break the speed limit of the universe, they completely ignore it? Enter tachyons, hypothetical particles that are said to always travel faster than light. According to some theories, these mysterious entities would never slow down to the speed of light or below, making them a fascinating, if speculative, concept in physics. But here's the catch: if tachyons exist, they would bend our understanding of space-time and causality in ways that seem almost impossible to comprehend. Imagine a particle that, instead of moving forward through time, could potentially travel backward, effectively reversing cause and effect. This isn't just a wild idea, it's a puzzle that challenges the very foundation of Einstein's theory of relativity. Why haven't we found tachyons yet? The simple answer is they remain purely theoretical. No experiment has ever detected a particle moving faster than light, and their existence would require a complete rethinking of the laws of physics as we know them. Still, the concept of tachyons sparks endless curiosity, pushing scientists to explore the boundaries of what's possible. And while they might remain in the realm of speculation for now, they remind us just how strange and unpredictable the universe can be. Still, the concept of tachyons sparks endless curiosity, pushing scientists to explore the boundaries of what's possible. And while they might remain in the realm of speculation for now, they remind us just how strange and unpredictable the universe can be. Speaking of strange, let's take a closer look at another mind-bending phenomenon, virtual particles. These fleeting, ghost-like entities pop in and out of existence, creating a bizarre dance at the quantum level that might just redefine our understanding of reality itself. Picture an empty void, the vastness of space seemingly devoid of anything at all. But in the quantum world, nothing is ever truly empty. Even in what we call a vacuum, particles are constantly popping into existence and vanishing just as quickly. These fleeting entities are known as virtual particles, and they're a bizarre byproduct of quantum mechanics. According to the Heisenberg uncertainty principle, energy can fluctuate in tiny, unpredictable bursts, allowing these particles to appear and disappear in pairs, one matter, one antimatter, before annihilating each other almost instantly. It's as if the universe is teeming with invisible activity, even in the emptiest corners of space. One of the most fascinating ways this phenomenon manifests is through the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, the space between them becomes too small for certain virtual particles to form. This creates a pressure imbalance, forcing the plates to move closer together. It's a direct, measurable consequence of quantum fluctuations, proving that even empty space is anything but. Another striking example is Hawking radiation, where virtual particles near the event horizon of a black hole can cause one particle to escape while its counterpart falls in, slowly causing the black hole to lose mass over time. Now here's a question to ponder. Could these virtual particles, constantly bubbling in and out of existence, actually affect the fabric of space-time itself? Some theories suggest that their energy might play a role in the mysterious force known as vacuum energy, a concept that connects closely to the dark energy accelerating the expansion of the universe. It's a mind-bending idea that opens the door to even deeper mysteries about the nature of reality. Did you know that even empty space isn't really empty? It's teeming with something called vacuum energy, a mysterious force that exists everywhere in the cosmos. This energy is a fundamental part of quantum field theory, which describes how particles interact. At every point in space, even in a complete vacuum, there's a tiny, fluctuating amount of energy. It's like a background hum that never turns off, and it's responsible for some of the most fascinating phenomena in the universe. One of its most significant roles is in the expansion of the cosmos. Scientists believe vacuum energy contributes to what's known as dark energy, the force driving the accelerated expansion of the universe. This means that even in the vast, seemingly empty voids between galaxies, there's energy at work pushing everything apart. But here's the mind-bending part: just how much energy is there in the vacuum? If you were to add it all up, the numbers are staggering, so immense that they challenge our understanding of physics itself. This leads us to an even bigger question. Could this vacuum energy be connected to deeper truths about the universe? Some theories suggest it might even tie into the idea of the holographic universe, where all the information in the cosmos is encoded on a two-dimensional surface. But that's a story for the next fact, and it's one that will stretch your imagination even further. Ever wondered if the universe we perceive is more like a hologram than the solid, three-dimensional reality we take for granted? The holographic principle, a mind-bending idea first proposed in the 1990s, suggests that all the information in our universe might be encoded on a two-dimensional surface, kind of like a cosmic projector screen. Think of it this way: just as a hologram encodes a 3D image on a flat surface, our entire reality could be a projection from a lower dimensional boundary. Recent research has added weight to this theory, with physicists exploring how black holes and their event horizons might act as these informational surfaces. If this is true, it could completely redefine our understanding of space-time, suggesting that what we see as depth and dimension might be an elaborate illusion. So, is our reality truly three-dimensional, or are we all living in a kind of vast cosmic hologram? This idea not only challenges our perception of the universe but also leads us to another fascinating concept, the Planck Scale, where the very fabric of space-time might break down into something even stranger. Have you ever wondered just how small the universe can get? At the tiniest possible level, space-time itself seems to break down into something entirely different, a realm known as the Planck Scale. This is where the fabric of reality becomes grainy, like the pixels on a screen, governed by the bizarre rules of quantum mechanics rather than the smooth, predictable patterns we're used to. The Planck scale is unimaginably small, so tiny that if you were to shrink a grain of sand down to this size, it would still dwarf the entire observable universe. But here's the catch: studying this scale is for now almost impossible. The energies and tools we'd need to probe such minute distances are far beyond anything we can currently achieve. It's like trying to read a book that's written in a language we haven't even discovered yet. So, what lies beyond the Planck scale? Could it be a completely new layer of reality, or perhaps the seeds of an entirely different universe? These questions lead us to one of the most intriguing theories in modern physics, loop quantum gravity. This idea suggests that space-time isn't just grainy but woven together in tiny, interconnected loops, creating a structure that might just redefine our understanding of the cosmos. Now, let's shift our focus to another fascinating contender in the quest to unify quantum mechanics and general relativity: loop quantum gravity. Unlike string theory, which envisions the universe as composed of tiny, vibrating strings, loop quantum gravity takes a different path. It suggests that space-time itself is not continuous but made up of tiny, discrete loops, like a woven fabric of reality. These loops form a network, and their interactions create the structure of space and time as we experience it. What's particularly intriguing about this theory is its approach to quantizing space-time. In loop quantum gravity, space isn't smooth but instead granular, with a smallest possible unit of volume. This granularity prevents the infinite densities that occur in classical black holes or the Big Bang, offering potential solutions to some of the most perplexing problems in physics. Imagine zooming in on the fabric of the universe. You wouldn't find a smooth surface but a mosaic of interconnected loops. However, like any groundbreaking theory, loop quantum gravity faces its own set of challenges. One of the biggest hurdles is reconciling its predictions with experimental evidence. While it provides elegant mathematical solutions, testing these ideas in the real world remains a formidable task. Additionally, the theory doesn't yet incorporate all four fundamental forces of nature, leaving room for further development. Still, its potential to redefine our understanding of space-time continues to inspire researchers. As we reflect on these competing theories, it's worth considering what they reveal about the nature of the early universe. Both string theory and loop quantum gravity offer glimpses into a time when space-time itself was just beginning to take shape, a topic we'll explore next. Picture this: the universe just moments old, bursting into existence with a singularity so dense and hot that it defies our understanding of physics. This was the Big Bang, the event that set everything into motion. But what happened immediately after? In those first fractions of a second, space-time wasn't the calm, predictable fabric we think of today. It was chaotic, fluctuating wildly, and expanding at an unimaginable rate. This rapid expansion is known as cosmic inflation, and it's a key piece of the puzzle when it comes to understanding the early universe. Inflation theory suggests that during this brief but intense period, space-time stretched exponentially, smoothing out any irregularities and laying the groundwork for the universe we see now. Without this process, the cosmos might have been a jumbled mess of clumps and voids, making the formation of galaxies and stars nearly impossible. Instead, inflation gave us a remarkably uniform universe, one where the laws of physics could operate on a grand scale. But here's the mystery: what caused this sudden, explosive growth? What set the stage for inflation to occur in the first place? That's a question even the brightest minds in cosmology are still grappling with. And as we ponder the origins of space-time, we're led to another fascinating possibility: cosmic strings. These hypothetical threads of energy, thinner than an atom yet incredibly dense, are thought to have formed as the universe cooled after inflation. Could these remnants of the early universe hold clues about the nature of space-time itself? The answers might be hidden in the depths of our cosmic past, waiting to be unraveled. Picture space-time as a vast, intricate tapestry woven together by the very fabric of the universe. But what if this tapestry had tiny, nearly invisible threads cut through it? Enter cosmic strings, hypothetical one-dimensional defects in space-time that could stretch across the cosmos like unimaginably thin and incredibly dense filaments. These cosmic strings are thought to have formed in the early universe, moments after the Big Bang, when the universe was cooling and undergoing phase transitions, much like water freezing into ice. During these transitions, tiny imperfections could have been frozen into the fabric of space-time, creating these bizarre and fascinating structures. Cosmic strings are theorized to be incredibly dense, with just a single inch of one potentially weighing as much as an entire mountain. Despite their immense mass, they're so thin that they'd be nearly impossible to see directly. But their presence could still leave ripples across the universe. For instance, if a cosmic string were to pass through a galaxy, it might create gravitational distortions, bending light in ways that could reveal its existence. Scientists have even suggested that cosmic strings could explain strange patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. But here's the big question: could we ever detect one of these elusive cosmic threads? The search is ongoing, with astronomers scouring the skies for subtle clues, such as unusual gravitational lensing effects or unexplained bursts of energy. While no definitive evidence has been found yet, the hunt continues, driven by the tantalizing possibility that these cosmic strings could unlock secrets about the universe's earliest moments. And speaking of time, let's turn our attention to another mind-bending aspect of space-time: its strange and often counterintuitive nature. What if time isn't the steady, unchanging force we've always believed it to be? What if it's more like an illusion, a construct that emerges from something deeper? This idea challenges everything we think we know about the universe. Some scientists suggest that time might not be a fundamental aspect of reality, but rather an emergent property, something that arises from the interactions of more basic elements. Think of it like the way temperature emerges from the motion of particles. It's not a thing itself, but a description of how things behave. In this view, time could be a byproduct of deeper physical processes, a way for the universe to make sense of change and movement. One fascinating theory that supports this idea is the block universe model. Imagine the entire universe as a four-dimensional block, where past, present, and future all exist simultaneously. In this view, time is like a landscape rather than a flowing river. Every moment from the birth of the universe to its eventual end is already there, fixed in place. It's a mind-bending concept that makes you wonder, do we truly experience time as it is? Or are we just moving through this block, perceiving one slice of it as the present? This raises a profound question. If time is an illusion, what does that mean for our sense of reality? Are we just passengers on a cosmic train, unaware of the tracks laid out before us? As we grapple with these ideas, we're led to another intriguing possibility: time loops, where the very fabric of time might fold back on itself, creating cycles that defy our linear understanding. But more on that in just a moment. What if the universe had a rewind button? Time loops where events cycle endlessly have fascinated scientists and storytellers for decades. Picture a moment in your life replaying over and over, like a cosmic video stuck on repeat. This isn't just science fiction, it's a concept that emerges from the bizarre realm of closed time-like curves, or CTC. These are theoretical pathways through space-time that loop back on themselves, creating the possibility of revisiting moments you've already experienced. In essence, a closed time-like curve could allow you to travel into the future only to circle back to your starting point, effectively trapping you in a never-ending sequence of events. But how could such loops exist? According to Einstein's theory of general relativity, the extreme warping of space-time around massive objects like black holes could create these curves. Imagine space-time as a flexible sheet under immense gravitational forces. It could bend so drastically that it twists back on itself, forming a loop. While this idea remains purely theoretical, it raises profound questions about the nature of time itself. Could our universe contain hidden pathways where time loops are possible? Or are these just fascinating thought experiments confined to the realm of imagination? This leads us to an even deeper question: what role does consciousness play in all of this? If time loops exist, would we even be aware of them? Or would our perception of time mask the endless cycles unfolding around us? Let's explore this intriguing connection between consciousness and space-time in the next part of our journey. What if our experience of time itself is a product of consciousness? This isn't just a philosophical musing. It's a question that some physicists and thinkers are starting to take seriously. One of the most intriguing speculative theories suggests that consciousness might not just exist within space-time, but could actually play a role in shaping it. Imagine for a moment that our perception of time's flow, the way we feel moments passing, isn't just a byproduct of the universe's structure, but a fundamental part of it. Some theories even propose that consciousness could be a kind of bridge between the quantum world and the larger fabric of reality, influencing how space-time unfolds at the smallest scales. Think about this: when we measure quantum particles, their behavior changes based on observation. Could consciousness be the key that locks these particles into specific states, weaving the threads of reality as we know it? This idea blurs the line between the observer and the observed, suggesting that our minds might be more deeply entangled with the universe than we ever imagined. While this remains speculative, it opens up fascinating possibilities about how we understand the nature of existence. Now, consider how this might connect to something like quantum computing. If consciousness can influence the behavior of particles, could it also play a role in the way quantum computers process information? These machines rely on the strange, counterintuitive rules of the quantum world, where particles can exist in multiple states at once. If space-time and consciousness are intertwined, could unlocking one help us master the other? This leads us to the next frontier, where the mysteries of space-time might just hold the key to revolutionizing technology itself. Quantum computing isn't just a leap forward in technology, it's a challenge to our very understanding of reality. At its core, a quantum computer operates on principles like superposition and entanglement, ideas that seem to bend the rules of space and time as we know them. Superposition allows quantum bits or qubits to exist in multiple states at once, defying the classical notion that something can only be one thing at a time. Entanglement, on the other hand, connects particles across vast distances instantly, as if space itself is irrelevant. These phenomena don't just push the boundaries of computing, they shake the foundations of classical physics, where space and time are rigid, unchanging frameworks. But what does this mean for the future? Quantum computers could solve problems that today's machines couldn't touch in a lifetime. They could simulate complex systems, like the behavior of entire galaxies or the intricacies of black holes, in ways that might unlock secrets of space-time we've only dreamed of. Could these machines one day reveal that space and time are far more fluid or even illusory than we've ever imagined? It's a question that bridges the gap between technology and philosophy, and it leads us to another mind-bending idea, the simulation hypothesis. What if everything we see, touch, and experience is nothing more than lines of code in a vast, intricate simulation? The simulation hypothesis is one of the most mind-bending ideas in modern philosophy and science, suggesting that our universe and even space-time itself could be part of an elaborate digital construct. Think of space-time as the fundamental framework of this simulation, acting like the underlying code that dictates the rules of reality. This isn't just science fiction. Thinkers like Nick Bostrom and tech leaders like Elon Musk have seriously entertained the idea, arguing that the odds of us living in a simulation could be higher than we think. The implications of this theory are staggering. If space-time is part of a simulated reality, then the laws of physics might just be the rules programmed into the system. Think of it like a video game. Just as a game has its own physics engine, our universe might have its own coded parameters that govern everything from gravity to the speed of light. This raises profound questions about the nature of existence. Are we, as conscious beings, merely characters in someone else's digital creation? Or could we, in some way, be the creators ourselves, plugged into a simulated world for exploration or entertainment? But how could we ever test such a wild idea? Some scientists suggest looking for glitches in the fabric of reality, tiny irregularities in the laws of physics that might hint at the underlying code. Others propose studying the behavior of particles at quantum levels, where the rules of space-time seem to break down in ways that could resemble computational limits. It's a fascinating challenge, blurring the lines between philosophy, physics, and even computer science. This theory forces us to rethink not just the nature of space-time, but the very essence of reality itself. If our universe is a simulation, what does that mean for free will, purpose, or even the concept of truth? As we explore these questions, we're led to even deeper mysteries about the fabric of existence, like what lies beyond the code, and whether there's a base reality that transcends the simulation. Have you ever stopped to wonder what reality actually is? When we talk about space-time, we're not just discussing the fabric of the universe, we're grappling with the very essence of existence itself. Theories about space-time and reality range from the wildly speculative to the scientifically grounded, each offering a unique lens through which to view the cosmos. Take string theory, for instance. It suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in multiple dimensions beyond the four we're familiar with, weaving a complex tapestry that defines everything we see and experience. Then there's the holographic principle, which proposes that our three-dimensional reality might just be a projection of information stored on a two-dimensional surface, like a cosmic hologram. It's a mind-bending idea that challenges our most basic assumptions about space and time. But here's the real question: which of these theories holds the key to understanding the true nature of reality? While string theory has gained traction for its elegance and mathematical consistency, the holographic principle offers a radical shift in perspective that could redefine physics as we know it. The truth is, we're still in the early stages of uncovering answers, and each theory brings us closer to piecing together the puzzle. As we dive deeper into these ideas, it's worth considering where space-time research is headed. What breakthroughs might we see in the next few decades, and how could they reshape our understanding of the universe? The journey to uncover the nature of reality is far from over, and every discovery brings us one step closer to unraveling the mysteries of space-time. As we peer into the future of space-time research, the tools and technologies at our disposal are evolving at an astonishing pace. One of the most groundbreaking developments in recent years has been the advent of gravitational wave detectors like LIGO and Virgo. These incredibly sensitive instruments have allowed us to listen to the ripples in space-time caused by cataclysmic events, such as black hole mergers and neutron star collisions. It's as if the universe itself is whispering its secrets to us, revealing phenomena we could only theorize about before. But this is just the beginning. What other mysteries might these detectors uncover as they become even more precise? On another frontier, quantum computers are emerging as potential game changers in our understanding of space-time. Unlike classical computers, which process information in binary bits, quantum computers use qubits that can exist in multiple states simultaneously. This allows them to tackle problems of immense complexity, such as simulating the behavior of space-time at the quantum level. Some scientists even speculate that quantum computers could help bridge the gap between quantum mechanics and general relativity, two pillars of physics that have resisted unification for over a century. Could these machines hold the key to decoding the very fabric of the cosmos? Looking ahead, the possibilities are as vast as the universe itself. Scientists are already dreaming up experiments that could probe the nature of dark energy, explore the concept of wormholes, or even test the idea that space-time might have a granular structure at the tiniest scales. The questions we're asking today: what is the true nature of time? Is space-time continuous or discrete? Might one day be answered by technologies we're only beginning to imagine. So, what do you think the next big breakthrough in space-time research will be? Will it come from a bold new experiment, a stroke of theoretical genius, or something entirely unexpected? The journey to uncover the deepest truths of the universe is far from over, and the discoveries waiting just beyond the horizon could reshape our understanding of reality itself.